Yeah, sure. Welcome to the third live section of Mechanics of Materials course. If you have any questions, kindly post it in the page. Sorry for the delay. There was a technical issue, so there was no internet connection. So we are joining through mobile network. Thank you. Yeah, sure. Welcome to the third live section of Mechanics of Materials course. If you have any questions, kindly post it in the page. Sorry for the delay. There was a technical issue, so there was no internet connection. So we are joining through mobile network. Thank you. Yeah, sure. Welcome to the third live section of Mechanics. If you have any questions, kindly post it in the pitch. Sorry for the delay. There was a technical issue, so there was no internet connection. So we are joining through mobile network. Thank you. Yeah, sure. Welcome to the third live section of Mechanics of Materials course. If you have any questions, kindly post it in the page. Sorry for the delay. There was a technical issue, so there was no internet connection. So we are joining through mobile network. Thank you. Yes, sir. Okay, again, sorry for the interruption. There was a technical problem. Okay, so we are going live now. Okay, so the one of the questions asked was what is the meaning of determinant of stress sensor? Okay, determinant of stress sensor tells you whether the state of stress is three-dimensional or two-dimensional or one-dimensional. Okay, if it is not a three-dimensional state of stress, then the determinant of stress will be zero. Okay, apart from this, there's no physical significance like determinant of deformation gradient, which will be the volume, which will give you the volume in the deformed configuration and things like that. Okay, so the determinant of stress tensor just tell you whether the state of stress is three-dimensional or of a lesser dimension. Okay, that is the meaning of determinant of stress tensor. Okay, and then there is a question on whether the spherical coordinate system are more suitable for what category of solid mechanics problems. Spherical coordinates are used to study inflation of a balloon and squeezing of a cone kind of problems, wherein you have it's not a conventional engineering problem wherein you solve using spherical coordinates. Okay, so some special boundary problems like squeezing of a cone, which will occur in case of a pre-stressed concrete beam at the edge zones. Okay, so you say you have a cone like this, which you want to squeeze, applying a pressure like that. For example, you can think of a cone ice cream which is being squeezed and the ice cream flowing out of the cone as a problem that you can study using spherical coordinate system. Inflation of a balloon is another example of a problem where you use spherical coordinate systems. Okay. So the coordinate system depends upon the geometry of the body, which is convenient to describe using which coordinate system to determine what coordinate system you are using to study the problem. Yes, rank also tells you what the dimension of the stress sensor is. Okay, determinant is one of the measures. The rank is precisely tells what is the dimension of the stress sensor. See, Kosterad theory of continuum, all this is more advanced level. Okay, I don't know much about that. It includes rotation as a degree of freedom in the formulation. So we can discuss it often if you are interested in such formulations. Any other questions? Yeah, equilibrium equation is balance of body forces and surface forces together, if you want to think it like that. But more appropriate way of thinking of it is it's the statement of Newton's second law of motion, wherein you say that the net force acting determines the direction of the motion of determines in magnitude and direction the acceleration of the body. Okay, so that is equilibrium equations. but in statics it can be thought of as the equation of equilibrium of body forces and surface forces. Okay. In real life problems, it is not that you have to decide between stress based or displacement based or a mixed approach. What is typically done is in the current scenario, you write the constellation, which is stress as a function of strain, right? So, displacement formulations are more computationally efficient. So you follow only displacement approach because there are only three components of displacement which needs to be found. Okay. So since there are only three components of displacements to be found versus six components in case of a stress formulation, such a displacement approach is found to be computationally efficient, and that is what is followed. We are trying to implement a computational scheme for solid mechanics problems. Okay. So it is not a question of a trade-off. But if you have implicit constellation of the form f of sigma, comma epsilon equal to 0, then the entire scenario is different. You need a mixed formulation to appropriately, easily solve the boundary problems. Okay, so it depends on the constellation, and the computational efficiency determines what is the independent variable you choose for solving a problem. Okay. Okay. Where can we get stress components as a function of x, y, and z to verify with equilibrium equations? See, the stress tensor can be written in terms of potentials, dou square phi 1 by dou y square minus dou square phi 1 by dou x dou y plus dou square phi 2 by dou z square minus dou square phi 2 by dou x dou z. Okay. Minus dou square phi 1 by dou x dou y dou square phi 1 by dou x square plus dou square phi 3 by dou z square minus dou square phi 3 by dou y dou z minus dou square phi 2 by dou x dou z dou square phi 3 by dou y dou z and dou square phi 3 by dou y square plus dou square phi 2 by dou x square. Okay, phi I are functions of x comma y comma z. Okay, so now this equation will see that will automatically satisfy the equilibrium equations. You can check dou sigma xx by dou x plus dou sigma xy by dou y plus dou sigma xz by dou z. If you want to verify this, it will be dou square p1 by dou x dou y square plus dou square phi 2 by dou x dou z square minus dou square phi 1 by dou y dou x dou y minus dou square phi 2 by dou z dou x dou z. Right? So if the order of derivatives were to be not important, when phi 1, phi 2 are smooth functions of x, y, and z, this will be equal to 0. Okay, you can see that this cancels with this and this cancels with that. Okay, so this is how you construct three-dimensional stress fields. Okay, these phi i's are called as Airy stress functions. Okay, so basically now this is how you construct the thing which will satisfy the equilibrium equations. Okay. So, any other questions? Okay, there's a question asking what is the use of Cauchy stress formula. Cauchy stress formula, I presume you mean that the traction expression. Okay, so why is it useful is it establishes the relationship between the normal and the traction acting on a cut surface. So you have a body, okay, say cut the body like this. The normal to this cut surface is say N. Now at this point, I am interested in finding what is the distributed force acting over that cut surface. Okay, so that may be denoted by attraction vector T of N here. Now the question is, how is this? What are the variables this T of N depend upon? It in general, it's a vector function which depends upon x, y, z, the coordinates of the point, time t, and the normal n. Okay, the Cauchy stress formula tells you how does this dependence on n is. Okay, it tells you it is linear. It comes from the fact that if I look at two halves of these cut body, this half and this half at the same point, this is n, and on the other surface it will be minus of n. Okay, the direction will be opposite. The magnitude is 1, so that will be minus n. Okay, and if the traction acting here is piece of n, traction acting on this surface would be piece of minus n. Okay, so t star of minus n. Okay, so now Newton's third law, now what it tells you is piece of n plus p star of minus n has to be equal to 0. Okay, that is these two should be in same magnitude, opposite in directions. Okay, so what it tells you then is for such a traction to exist, it should be a linear function of n. Okay, or it should be an odd function of n, and Cauchy shows that it should be a linear function of n. Okay, that is the utility of the Cauchy's stress theorem, as they call this as. It can be shown under certain assumption that this is how the traction and the normal would be related to each other. Okay, I presume you know what traction is by now, having done the course. It comes in the first half of the course. Okay, now from this formula only you compute what the traction acting on any of the cut surfaces are. Okay, it is also used to see how the stress sensor transforms due to coordinate transformations and all those things. Okay, okay. There's a question on what is the physical meaning of complementary strain energy. See, energy per se doesn't have a physical meaning. it is a mathematical construct, just like force is a mathematical construct to explain the displacement of bodies. If you don't want to use forces, you use energy-based approaches. Then energy becomes a fundamental quantity, which is given an equal footing as the forces, which is a mathematical construct. Okay, so you can motivate the force by lifting a weight or by pulling moving a car down the slope and things like that, right? Similarly, energy can be motivated by its capacity to do work. Okay, so basically, in that sense, if you are to write the energy as a function of strain, then it is just strain energy. On the other hand, why should you write it as a function of strain? You can write it as a function of stress also, right? Write it as a function of stress, it becomes the complementary strain energy. The reason being, in one dimensions, if you look at strain as a stress plot along a particular direction, this is a strain along a particular direction and this is a stress along a particular direction. Okay, so what happens is you have a curve something like this, say. If I were to integrate with respect to the strain here, I will get this area in here. This area in here is called as the strain energy. On the other hand, if I were to integrate with respect to the stress, what is the area I will get? I will get this area. I get this area, which is the complementary strain energy. Strain energy. Okay, so that is the reason why both of them are together to give you the stress times the strain. Okay, strain energy plus complementary strain energy will give you the area product of the stress and the strain. All this happens fine, but in 3 dimensions there are certain issues which we can't get into at this point in time. Okay. Okay. Okay, stress invariant is invariant under any coordinate transformations. Okay, it is the innate property of the second order tensor. Any 3 invariants that you use is the innate property of second order tensor. It need not be stress, it can be strain, it can be moment of inertia, it can be any second order tensor which has a physical meaning or no physical meaning also. If it is the invariance won't change under coordinate transformations. Okay, so basically, why do you need them is you can't have quantity which depends on a coordinate system. For example, if I take this body, if I pull this body and if it fails, the failure load doesn't depend upon what coordinate system I use to analyze this problem, right? So that's why the failure theories are based on the invariance of the stress tensor. Okay, so that is the reason why you have to have invariance, and invariants are used to model the failure of a body or to come up with quantities which are devoid of dependence on the coordinate system. Okay, it doesn't change with coordinate systems. Okay. Okay, there's a question on why you are not considering the internal forces when I write the equilibrium equations of a beam. See, only when I cut the beam, I have to expose the internal forces, right? So if I take a beam subject to a point load, and I say it's simply supported in here. I say it's simply supported in there. Okay. So what? There's no reaction force coming here. No. What I do, I remove the support and then model the beam, draw the free body diagram of the beam. Only then I have this load P. I have this reaction force RA, HA, and I have this RB. Okay. Now, if I don't cut it at the support, instead I want to look at this part of the beam alone, say. Instead, I want to look at this part of the beam alone, say. Then what will happen is, I will have a support reaction here, RA, HA, and I will have a distributed force acting like this, which is the axial force. I'll have a distributed force, which is the axial force. Acting like that, and I'll have in addition to that another distributed force, which is a shear force, acting like this on the cross section. This sigma, or let me call it as just the shear stress. This will be normal stress, sigma xx, say. Okay, if I were to denote this by x, y, and z, the shear stress will be sigma xy. Okay. Okay. So now I have to look at what this distribution is, what this moment is, what is this shear force, what this moment is, what this shear force is. Okay. For that, I have to solve the problem as a deformable body. Okay. Strain energy is in fact a form of potential energy. Let me illustrate that through an example. Uh, Forget a beam bending. Let's say I have a steel rod and I place a weight W on top of it. Okay, place a weight on top of it. Place a weight W on top of it. What will happen? This steel bar is going to now shorten a bit. I draw it exaggeratedly, shorten a bit like this, and this weight is going to move down to this mantle, right? Now let's say this deflection is delta. What happened? The weight has moved down by distance delta. So mg is W. Okay, mass times acceleration due to gravity is W. So that is the weight of that mass. Okay, so now I have W times delta would be the potential energy lost or potential energy of that thing which is moved down. Okay, and what is the strain energy of this bar? Strain energy of the bar strain energy of the bar would be integral E times epsilon d epsilon. Okay. Epsilon d epsilon 0 to epsilon. Okay. Or you know that strain energy due to the bar would be what? E epsilon square by 2 into dv. I have to do it for the entire volume of the body. Okay, so that will be E times delta by L is epsilon. Let's say initial length of the bar was L. Okay, delta by L square by 2 to L into cross sectional area is the total strain energy of the bar. Okay, that will be EA delta square by 2L. Okay, now EA into the EA delta into delta by 2L. This is nothing but W into delta by 2. Okay. EA into delta by L is a strain. E into strain is a stress. Stress into A is a force. That force is W. So it will be W delta by 2. Okay. So what has happened? By moving down, the mass has lost potential energy of W delta, whereas the energy stored the system is W delta by 2. Okay. So what happened to the remaining W delta by 2 is a classical question that someone can ask. Okay. The reason why there is a difference of W delta by 2 is because in computation of strain energy, when you say that it is integral E epsilon, integral D epsilon 0 to epsilon, you are assuming that the load is applied gradually. In which case the potential energy loss won't be W delta. Okay, it is applied gradually, which means I'm applying a load delta W, increasing it to 2 delta W, increasing it to 3 delta W, and that's how I get the strain in the bar as E epsilon D epsilon 0 to epsilon. Okay, that is sigma D epsilon, right? Sigma dot D epsilon, right? So that's why you get this 2 in here. Okay, that's why you get this 2 in here. Otherwise, you won't get that 2. Okay, so similarly, you can't talk of the potential energy lost of a system alone. That will be commensurately, there will be a gain in the strain energy of the system also. There will be a difference between the two, and that is what you are looking at in energy methods. See, the stress cracking due to corrosion is not dependent on the strength of the material alone. It depends upon certain other factors also. So, strength of the material alone doesn't mean that you have better chance of not cracking due to stress corrosion. Okay. Our potential energy is stored in the beam. If I have a beam and there's a energy stored in the beam also, same energy stored in the beam also, which will depend upon the bending moment m square by 2 EI dV. EI. Okay, let me derive that for you. Okay, so basically now what sigma in case of a bending is given by m by I into y. Okay, m by I into by y, or I have to write in terms of the curvature now because I'm talking about the strain energy. So strain energy for sigma by y equal to m by I equal to E by rho or ER or E phi Okay, that is the radius of curvature. So sigma is EI into phi, where phi is the curvature. EY into curvature. EY into curvature, right? Okay, so what is the energy, strain energy then? Strain energy would be EY into phi, which is d square delta y by dx square into d phi integrated over the volume. 0 to phi, and this I have to integrate over dv. Okay, so this will be EY phi square by 2 into y d phi units are not constant. Okay, y d phi is a strain. Strain was y minus y d square delta y by dx square, right? This is the curvature phi. Okay, so now if I were to integrate over dA, and this over dx, y square dA is EI p square by 2 dx, 0 to L. Y square dA is the moment of inertia I, so I have EI phi square by 2 dx. So EI phi is bending moment, so I can write it as m phi by 2 into dx. Or I can write similarly for phi also, I can substitute, and it will be m square by 2 EI dx would be the strain energy stored. That will be the complementary strain energy. Since the linear response, but the complementary strain energy and strain energy will be the same in this case. Okay. So that's how you compute the strain energy in a beam. Yes, the strain energy will take care of the change in the potential energy in the beam also. Okay, how to compute the deflection of thin-walled cross section? Thin-walled tube section subjected to what? It's not clear whether unsymmetrical is fine. Thin-walled tube section subject to torsion or bending moment is something that you have to let us know. Okay. There's no absolute datum for potential energy, it's all relative. Okay, so the incremental energy is what you can measure. You can't measure the absolute energy. Any other questions? Uh, it is not, strain energy is not necessarily due to the elastic forces. even when the material is deforming plastically, there will be some energy stored. Even in a viscoelastic material, there will be energy stored, especially in solids. So it is not only due to elastic forces. Okay, so it is the energy stored in the system is the strain energy. The nomenclature is a misnomer. It is better to call it as stored energy rather than strain energy. Okay. So basically, the energy that is stored in the system has to come from somewhere, right? Energy can't be created nor destroyed. Okay. So basically, that's why there's a conservation of energy principle. Okay. Any other questions? Okay, rectangular bar torsion is you can look up advanced solid mechanics in NPTEL. NPTEL web course, or I have by me. Okay, there I derive the expression for torsion including the warping. Okay, so what happens briefly here is the displacement field will be given by a different expression, Ex plus omega xz Ey plus a warping function x comma y. Okay, Ez, and then you have to find this is the warping function. You and then introduce a Prandtl stress function phi such that stress is given by zero zero dou phi by dou y, 0 minus dou phi by dou x, dou phi by dou y minus dou phi by dou x, 0. Okay, and then you relate the phi to the psi, and then you'll get certain governing equations and boundary conditions from which you'll find that you can find what the warping function is. And in general, if the section warps, it will have a stiffness lesser than what is given by the polar moment of inertia. Okay, so now I don't have time to run through the entire derivation, so I request you to look at the NPTEL web course on advanced solid mechanics prepared by me, wherein you can see the detailed derivation of torsion. Okay, strain, see, energy has to be conserved. So energy should flow from somewhere to somewhere else. So if the strain energy of the system increases, for example, when I in this problem, when I place a bar, there's a loss in the potential energy which went to be stored as the energy in the bar. Okay. Now think of a reverse problem wherein I just remove the W. I remove delta W1, delta W2, delta W3. What will happen? The bar is going to come up again. Okay. So what happens there is the strain energy in the body is doing a work now to lift this bar from here to delta, here by delta. Okay, so there's a potential energy gain. Okay, which is what is coming at the expense of the energy stored in the bar as a strain energy. Okay. Okay. So basically, it is conserved. So somewhere the energy has to decrease, somewhere the energy will increase. Where it decreases, where it increases is depends on the system that you are looking at. Okay. Necking is not found in torsion testing, but it is found in uniaxial testing. That's because the shear stress governs the failure. Okay, in the torsion, the maximum shear stress occurs in the plane of the twist. Okay, whereas if I do a uniaxial test, where does the maximum shear stress occur? Maximum shear stress occurs at 45-degree plane. Okay, so the metal has to slide like this, and hence it doesn't, it necks. Okay, so because the shear stress counts the failure, and the necking happens in a uniaxial test. Okay, so in fact, in the video lectures, we would have seen the plane of slip for a one versus criteria that will be different from 45 degrees. Whereas for a Triska criteria, which is governed by maximum shear stress criteria, will be at 45 degrees. Okay, so these things you can judge from what stress governs the failure and how it fails. Will determine how it fails. Yes, strain energy is stored as an internal energy. Okay, how to capture the load displacement curve of a frame structure at post collapse? According to me, post collapse behavior that you get experimentally depends upon the frame characteristics also. It's not something dependent on the frame alone, because it depends on the radius difference between the testing frame and the frame that you are testing. Okay, what I mean by testing frame is you have a rigid frame here, right? You have a rigid frame, a strong floor on which you're going to do a frame test. Say I'm doing a frame test of a connection. I'm applying a force like this, and I'm applying a force like this, say, through an actuator. Okay, so the stiffness of this beam, this column, also determines the post peak response. Okay, uh, so it's not so straightforward to that you can capture that easily, but there are mechanisms of doing it. I can't get into those things right now. It's not that plastic deformations are irrecoverable. You have to do a thermal cycle to recover the plastic deformations. See, buckling load will automatically tell you if it is a shear buckling, you have to use the shear modulus. If it is the normal force, normal stress which causes a buckling, you have to use the Young's modulus. Good question. For deriving beam theory, we assume pure bending, which is not satisfied in cases where we apply the formula. Actually, go out and apply. That's the versatility of the theory. That's how good the theory is. Even though it is not applicable, it is nearly accurate. Okay, so that's the power of idealization. Okay, so you can't make a problem much more simpler than what it is or complicated than what it is required to be. Okay, so you apply beam theory on cases where you don't satisfy all the assumptions also. But there are certain assumptions like homogeneity. If you have multiple material connected together, there you have to make sure the assumptions are satisfied. But plane section remain plane is an assumption where you get it through even if the metal is inhomogeneous, deforming plastically, deforming viscoelastically, and so on. And it has been experimentally also verified that plane sections do remain plane. Okay, so basically that is an assumption that you make which is universal, but other assumptions are to be satisfied. Any other questions? Torsion equation is much more not as general as the beam bending equation. It holds only for closed sections, wherein there is this expression, especially P by J equal to shear modulus times the angle of twist per unit length, the shear stress by R, holds only for a closed section where there's a continuous flow of the shear stresses. And that is violated, which is the case in most sections. You can't use the elementary theory to predict the response of the structure due to torsion. It's very approximate. Okay, you have to appeal to theory of elasticity to be able to get a accurate expression for torsional moments. Any other questions? See, principal stresses, you don't need a software to find the principal stresses. Okay. You have to find, especially in three dimensions, you'll have the characteristic equation, a cubic equation, which you have to solve. That in most cases will be boiling down to a quadratic equation. Okay. Any program which can find the eigenvalues of a given matrix is good enough to find the principal stresses. Okay, MATLAB does it, Mathematica does it, Maple does it, LinPack in C++ will do it. So there are many ways by which you can do find the principal stresses. Any other questions? You can use the beam theory pretty much. That is how all the buildings are built. Okay, so how accurate it is depends upon how you are applying it and how you are mm, idealizing the structure. Okay, so that can't be explained here. Any other questions? Yeah, I'll take one more question and then we'll stop for the day. I know we began a bit late, so I extended it by 15 minutes. So if there are any more questions apart from one more last question, please post it on the forum. We'll answer it as soon as possible. Yes, the eigenvalues represent the principal stress. The eigenvalues of a stress tensor represents the principal stresses. Okay, what is the meaning of three principal stresses is, see, they represents the uh, maximum stresses, maximum normal stress that occurs uh, at that point, and the principal directions gives you the direction on which these maximum normal stresses occur. Extremum normal stresses, maximum as well as the minimum. Second one is in between thing, which is not of much use. Okay. The three principal stresses represents the maximum normal stress and the minimum normal stress that occurs in a particular for a given stress tensor. The principal directions represent the direction on which the maximum normal stress and the minimum normal stress acts. Yeah, you can derive the analytical torsional rigidity for a three-layered isotopic beam. I think if you refer to advanced mechanics of NPTEL notes, you should be able to do that for a rectangular section or for a circular section, whatever the cross section is. Okay. Any other questions? So I think it is time. We'll close the thing in another 1 or 2 minutes. Yes, you can. There's no maximum and minimum shear stress. There's only a maximum shear stress. Maximum shear stress would be the difference between if sigma 1 greater than sigma 2 greater than sigma 3, tau max would be sigma 1 minus sigma 3 by 2. So all that you need is a maximum and a minimum principal stress alone, absolute value of this. Okay, that will be the maximum shear stress. The minimum is always 0 because you know that when the principal stresses occur, the shear stress on a plane is 0, right? So that's why it will have 0, and this maximum shear stress will have both positive as well as the negative directions because of the complementary nature of the shear stress. That's how the shear stress is, right? Tau. So if this is positive, this is negative, right? So basically, it doesn't make sense to talk about positive shear stress or negative shear stress. Shear stress, you talk only about the magnitude of the shear stress, and then there is always a plane ends which has a 0 shear stress, which will be the principal plane. So shear stress varies from 0 to this maximum value, or 0 to negative of this maximum value. Okay, so you always talk about only the maximum value of the shear stress, not the minimum value of the shear stress. Okay. Any other questions? We or we'll close. There are a lot of interesting questions asked in this section, so I thank the participants for doing that. Okay. So post any more questions that you have in the forum. So we'll wind up for this session. Okay. Thank you.